Welcome back to another immersive cybersecurity walkthrough. Today, we are focusing on one of the oldest, yet still one of the most destructive vulnerabilities in the web application landscape, SQL Injection, or SQLi. This is part of my Hacktify Cybersecurity Internship series, and in this session, I guide you through my hands-on labs, real-world examples, and mitigation techniques to protect your applications. Before we dive in, let me remind you that this video is for educational purposes only. Everything we're covering is intended to help you understand vulnerabilities and defend against them, not to exploit systems unlawfully. Always test in environments where you have explicit permission. Also, a detailed write-up with all the labs and technical insights is linked in the description, both on Medium and GitHub. Make sure to check it out for deeper learning. Let's start by understanding the foundation. SQL injection is a code injection technique where attackers place malicious SQL statements into application inputs to manipulate the backend database. When an application does not properly sanitize or parameterize user input, these injections can bypass authentication, extract sensitive data, or even alter records. According to the OWASP Top 10 for 2024, SQL injection accounts for nearly a fifth of all web application attacks globally. And this isn't just theoretical. In September 2024, researchers uncovered a severe vulnerability in the Flycar system, which services smaller airlines and interfaces with the TSA. Attackers exploited an SQLi flaw to add fake pilots to airline rosters, potentially bypassing security and accessing aircraft cockpits. Real-world consequences, real-world risks. Let's talk about the different types of SQL injection attackers use. First, the classic SQL injection. This is where attackers directly inject malicious SQL code into user inputs that are concatenated into backend queries. Next, blind or inference SQLi. In these cases, the application doesn't display obvious errors, but attackers can still deduce information based on how the application behaves. Think of it as asking yes or no questions to slowly map out the database. Then, error-based SQLi. Here, attackers rely on verbose error messages from the database to reveal sensitive information like table names and structures. Union-based SQLi is another method, where attackers use union SQL statements to merge malicious queries with legitimate ones and extract data from additional tables. There are also time-based and out-of-bounds SQL injections, as well as database-specific variations, all of which exploit unique behaviors of different database engines. Now, let's get practical. I'll walk you through the labs I completed in this series, step by step. In the first lab, titled Strings and Errors Part 1, we found vulnerable fields by examining the page source. There, a comment hinted at the payload, one quote, or 1 equals 1. Using this payload in both email and password fields granted full access to the admin panel, including credentials in plain sight. This confirmed the application was blindly trusting user input. Moving on to Strings and Errors Part 2, we spotted an ID parameter in the URL. Appending an extra single quote exposed SQL errors, and by crafting a union select statement, we retrieved the database schema, confirming the application's vulnerability to union-based attacks. In Part 3 of this series, we went a step further. By refining the union select query to pull usernames and passwords from the users table, the application returned admin credentials once again. These raw, unsanitized queries make it dangerously easy for attackers to escalate privileges. Next, Let's Trick MLab explored how login logic can be broken using SQL injection. Testing the input fields with single quotes revealed errors, and by inspecting the source code, I found a payload structured as one quote or 1 equals 1. Entering this in both fields allowed us to bypass authentication entirely. Now, let's talk about the Booleans and blind lab. By appending specific payloads to the URL, we could see differences in application behavior, revealing sensitive information through blind inference. In the error-based tricked lab, payloads embedded in both email and password fields allowed us to manipulate query logic and gain admin access. This confirmed the presence of unsanitized input fields vulnerable to error-based injection. Errors on post explored vulnerabilities in post parameters. Modifying these with the same injection payload granted access without credentials. This means the server-side logic failed to distinguish between safe and malicious input in post request. Next came user agents leaders. SQL injection wasn't limited to form fields or URLs, it extended to HTTP headers as well. Modifying the user agent header to include injection payloads caused SQL errors, confirming that the application was logging or processing headers unsafely. Referrer leaders was similar. By tampering with the referrer header in intercepted requests and inserting payloads, we observed SQL errors and unexpected responses. This showed that the application was incorporating referrer header data into its queries without validation. Then came cookies, where I injected payloads directly into session cookies. After modifying the username cookie with a union select payload, the application disclosed the database version, user, and name, proving that cookies were vulnerable entry points. Finally, we tested WAFs are injected and WAFs are injected part 2. Here, even with a web application firewall in place, we managed to bypass protections using obfuscation techniques. Payloads like plus signs and specific param manipulations helped evade detection and successfully extract sensitive data. So, what can we learn from all this? Let's go over best practices to protect against SQL injection attacks. First, always use prepared statements with parameterized queries. This is the single most effective defense, ensuring user input is treated strictly as data, not executable code. Second, suppress detailed error messages. Exposing stack traces or SQL errors gives attackers a roadmap to your database. Third, treat all external data as untrusted. Whether it comes from form fields, headers, cookies, or URL parameters, validate and sanitize it rigorously. Fourth, ensure your database account uses the principle of least privilege. Even if an injection succeeds, limited account privileges can drastically reduce the damage. Fifth, keep your web application firewall rules up to date, and don't rely solely on WAFs. They are an important layer, but they should complement, not replace, secure coding practices. Sixth, always employ allow list validation. Define strict patterns for acceptable inputs, and reject anything outside these constraints. Seventh, perform regular penetration testing. Both automated tools and manual reviews are critical in identifying weak points in your application's defenses. Lastly, educate your developers. Awareness and understanding of these vulnerabilities make it far less likely they'll be introduced in the first place. A complete write-up of all these labs, along with the payloads and technical explanations, is available in the description. Check out the Medium article and GitHub repository to follow along and practice safely. Before we wrap up, let me say this once more, this video is for educational purposes only. Do not attempt these attacks on any systems where you do not have explicit permission. If you've encountered SQL injection vulnerabilities in your own projects, or if you have any questions, drop them in the comments below. I'd love to hear about your experiences and help answer your queries. If you're passionate about cloud security, penetration testing, or ethical hacking, connect with me on LinkedIn, or check out my GitHub for security-focused projects. Thank you for watching, stay curious, stay safe, and I'll see you in the next tutorial.